Dear colleagues, let me introduce our joint research team. From Igor Sikorsky National Technical University KPI, Professor Alexei Yanenko, Professor Konstantin Shevchenko, Docent Sergei Peregudov, and from Alexander Bogomolets National Medical University, Professor Corresponding Member of the National Academy of Medical Sciences of Ukraine, Vladislav Malanchuk, and Docent Alexander Golovchanska. The subject of the represented study is assessment of dielectric implantable biomaterials compatibility based on the level of low-intensity millimeter range signals. The modern medical technologies use a great number of the natural and synthetic biomaterials, synthetic polymers, bioceramics, bioglass, metals, as well as metals with outer dielectric coating, including nanomaterials. For correction of bone defects and soft tissue regeneration, the hybrid materials are also used. They include materials of non-living nature and biotissue cells and organs. Any biomaterial interacts with the organs and tissues of a living organism and can become the cause of undesirable consequences. To avoid this, many biocompatibility criteria must be met, for example, corrosion resistance, chemical stability, biological tolerance, antimicrobial properties. At the same time, interaction through the electromagnetic field is not taken into account, although any physical body is known to be the source of the electromagnetic radiation. It's also known that millimeter-range electromagnetic waves are capable of affecting bioobjects. The authors propose a new approach to assess the electromagnetic compatibility of an implant with biological tissue. The living body thermodynamic balance is constantly changing due to the flowing bioprocesses. As a result of these changes, a part of the energy will transform to the electromagnetic radiation energy, transmitted from biotissue to implant or backwards. According to Planck's law, the spectral radiation density of a heated object in the millimeter range is defined by Formula 1, where R is the radiance coefficient, and it is taken into account that the radiometer is capable of detecting radiation of one main mode. For millimeter range and human body temperature, Formula 1 transforms into Nyquist Formula 2, and the power measured by the radiometric receiver can be determined by Formula 3. Here, delta F is analyzed by receiver band. Taking into account the peculiarities of radiometric measurements and different radiance coefficients of biological tissue Rb and implant material Ri, it's possible to record imbalance of their radiation power, Formula 4. This imbalance could interrupt metabolism processes in tissues surrounding implant. Since millimeter range radiation significantly affects living organisms, it's important to determine Rb and Ri for this range. The surface density power of dielectric bodies and liquids in the millimeter range at low temperatures is 10 to minus 12, 10 to minus 13th degree watt per square centimeter, and for the human body it is 10 to minus 13, 10 to minus 14 degrees watt per square centimeter. It's also necessary to take into account the difference between the permeability values of the tissue and biomaterial, and to estimate the reflection coefficient gamma. Therefore, it's an important task to study the radiation and absorption capacity of biomaterials and to compare them with same characteristics of human biotissues. The radiative characteristics of three types of objects were studied: biotissue as bone powder, hybrid biomaterials, osteoblast K, osteoblast T, polyhemostat, and synthetic biomaterials, calcium salt of orthophosphoric acid, bioactive glass and bioceramic material, and two-phase ceramics based on hydroxyapatite and precalcium phosphate with different particle sizes. Before each study, two respondents' own radiation was measured for comparison. When making measurements, it should be taken into account that the millimeter range waves are much weakened in water and air. Therefore, the receiver must have a high sensitivity and the experimental sample must be placed near the antenna. In addition, samples must be screened from an external electromagnetic background. Studies of implantable materials were executed in the Laboratory of Microwave Radiometry of the Igor Sikorsky National Technical University, KPI. Studied samples were provided by a team from Alexander Bogomolets National Medical University. A high-sensitivity radiometric system of the millimeter range was used. Its sensitivity threshold is 3 multiplied by 10 to minus 14th degree watt per square centimeter. A block diagram for the radiation level study includes an automated device for heating and highly sensitive radiometric system with the receiving antenna and input attenuator. An overview of the input unit of the radiometric system is shown on this slide. The radiation level was measured at frequency 52 GHz. At the same time, the temperature of the experimental sample was about 37 Celsius degrees. Based on the result of the measurements, a comparative diagram of the levels of natural radiation of materials was created. Materials represented as samples from 1 to 4 have a relative coefficient of radiation ability comparable with the level of radiation ability of a human. It is logical to assume that these materials will interact more physiologically with the tissues of the human body, and their use may increase the effectiveness of treatment. The absorbency of materials was also studied using a radiometric system. However, the input circuit of the system has been changed. The experimental samples were irradiated with the output of the millimeter range generator G. The radiation level was controlled by the attenuator A1 and the reflected signal level by the attenuator A3. The direction of these signals is controlled by the directional coupler A2. The power measured by the radiometer characterized the absorbency of the material sample. The absorption capacity is defined in several steps. Initially, a calibration of the measuring setting is performed. The antenna is closed by a metal plate and the attenuator A1 sets the necessary level of the irradiation signal P1. The readings of the attenuator A3 were recorded. Then the material sample is placed under the antenna. The attenuation of the attenuator A3 was set so that the radiometer indicator reading was the same as that of the calibration. A radiometer measured the power of the reflected signal P2. The return loss value was calculated by Formula 6. It characterizes the absorption ability of the biomaterial. A comparative diagram of return loss of materials was created. The difference in the level of reflection losses of natural materials, samples from 1 to 4, is in the range of 5 to 10 dB relatively to the level of synthetic materials, samples from 5 to 10. This slide presents the main findings of the research. In our opinion, biomaterials should be selected taking into account the factor of their electromagnetic radiation, considering interaction with biotissues. Thank you for your attention.